Okay, so let's start. Now we're officially into the second half, which is the solving differential equations. Let's just warm ourselves up and change the gears and talk about finding all solutions to the following problem: y double prime t equals to 12t squared. Okay, so let's see. First, let me say that I can make some guess. Okay, how do I guess that? I have a function whose second order derivative is a quadratic polynomial, and therefore probably I can try a quartic polynomial. Let's say yt equals to say some t to the fourth. Then I just take a derivative, y prime t. This is 4t cubed. Y double prime t is 12t squared. Bingo. So seems to be this is one solution. But the question is whether these are all the possible solutions. So let's see. Who thinks that this is the unique solution? Okay, 70%. Most of you, indeed, as you can see, think that the solution shouldn't be unique. It is indeed correct. Because let's say I can easily find some other solutions. Let's say yt is equal to 1. If yt equals to 1, then y prime t is already 0. Therefore, y double prime t is 0. So this means I make a linear combination. So this is t4 plus any number c is in R, is going to be a solution. Now let me change the question. Who think these are all the solutions? I mean, I already have infinite number of solutions. Okay, so seems like a growing number of you thinks that these are all the solutions. So let's take a look. Let me give you another example. So yt equals to t. Now indeed, y prime t is 1, not 0. But y double prime t is 0. Now it means that if I mix this with any c1t, because I just scale it, it doesn't matter, plus any c2, where c1, c2 are real numbers. I mean, this indeed, every function of this form will be a solution to this differential equation. Turn the question again. Who think that these really include all the solutions? Okay, so now most of you really think this include all the solutions. It is correct. But it's really, I have to say, at this point, it's not that clear why this must include all the solutions. How can I be sure that no other function of any form would be able to satisfy this differential equation? I mean, there are infinite number of choices of the functions, and as we learned in chapter 4, the space of all the second order differentiable functions, and that should be infinite dimensional. It's not only an infinite number of them, but it's actually infinite dimensional, because 1, t squared, t cubed, t fourth, so on and so forth, each of them is linearly independent from before. So it's an infinite dimensional linear space. How can we be sure there is no other solution? So let's see, let's draw an analogy. With the question of solving linear systems, AX equals to B. We actually faced a very similar question before. Is there a unique solution? Are there an infinite number of solutions? How can we characterize the solution set? So if the question is of the form AX equals to B, we actually proceeded in 2 steps. One is to find a particular solution, which is called XP. P stands for particular. So I put a vector sign here. So this one, it doesn't matter how I obtained that. It could be I guessed it. It could be that I used row elimination and converted things to the row echelon form, and so on and so forth. Anyway, I got a solution. 2 is I look at the homogeneous equation of the form AX equals to 0. Maybe the solution is unique, then the solution set to the homogeneous equation will be trivial. But anyway, I can obtain a solution set, I call it W. And this W is a subspace. Then we concluded that all solutions must be of the form XP plus a vector W, where W is the subspace W, the solution to the homogeneous equation. So there's no other possibility, and we proved this in chapter 1. So the situation is very similar here. If you look at the left-hand side, so I have a y t. So this one, you can think this is an operator. This is an operator. Let's call it t. T maps a function in a space V to V. What is V? So V, let's say, is the vector space of infinitely differentiable functions. On R, we can consider some other vector spaces, but this one's the simpler. And this is still infinite dimensional space because of t squared, t cubed, and all of them are linearly independent. And what it does is to take a function yt, map it to y double prime t. So this is indeed a mapping from V to V. Right? Y is infinitely differentiable, means that any arbitrary order of the derivative exists. Then I take 2 derivatives. It's still an infinitely differentiable function. So indeed, the t maps from V to V. And what we're asking is, when do we have ty, y, this vector thing, means this yt equals to some b, where this b is really right-hand side is 12t squared. Any question? Everyone understands what I'm talking about here? Very good. So let's recall in this little bit more abstract language, what were we doing? First of all, we want to make sure that t is still linear. You give me any two functions. Let's call it y1 and y2. This is doing is a1 y1t plus a2 y2t double prime. So this is a1t y1, a2 t y2. So this is indeed linear. We're back to linear algebra. And we want to find a specific, a particular solution. A particular solution is our yp, and this is t to the fourth, right? So this is what we found before. In order to find all solutions, we need to solve the homogeneous equation, which is t y equal to 0. This is the same as y double prime t equal to 0. So how do I solve this thing? I can just do integration. So let's see, this means that y prime t should be a constant. Let's call it C2. C1 means that yt should be C1 plus C2t, right? So these are all the possible, all homogeneous, all solutions to the homogeneous equation. And therefore, the solution set is really the particular solution plus a homogeneous solution. Any question? Yeah, there's a hand.
Professor, when we integrate C1, when we get C1t plus C2,
C1t. Yeah. Any other question? And you might say that, well, this is really complicated, right? I mean, a much simpler and way, which is from calculus 1a, I know y double prime equals to 12t squared, and I just integrate. I know it is a second order thing, so I just integrate once, I have a C1, integrate 2, I have C2, and that's it. So of course, that would be the right way to do it. But you can see that before in the, so if you really think at the 1A level, I mean, this seems to be just a mechanical procedure to do it. But now you can take this slightly higher perspective of this quite seemingly mundane problem, and you find that the concept of linear algebra actually applies pretty naturally. Indeed, the solution takes the form this t to the 4 by integrating this one is a particular solution, and these two are coming from the solutions to the homogeneous system. Any question? Okay, so look at another problem. So this is y prime t equals to lambda yt, where lambda is just some r. Let's try to solve this. How do I solve this thing? I first, the solution, I first realize this requires some guess. I consider this particular function, which is a function of t. I take a derivative of it. This one, by the Leibniz rule, so this is minus lambda exponential lambda t, yt, plus exponential minus lambda t, y prime t. This is a common factor. Inside is y prime t, minus lambda yt. This is exactly the equation. So equal to 0. So the whole thing is equal to 0. Therefore, we have exponential minus lambda yt equal to a constant and called c. This allows us to solve the problem lambda t. So for every lambda, actually not only lambdas in R, lambda, if lambda is complex number, that still works. What is this doing? This one, again, if you consider this more abstract setting from V to V, map any function yt to its derivative, then what we're talking about here is eigenvalue problem. So as you recall, in chapter 5, the eigenvalue problem for given matrix A, let's say it's n by n matrix, is number of eigenvalues would be smaller than or equal to n, even if you count multiplicity. However, in this case, for any lambda in R, in fact, C, this is eigenvalue. Why? Because there's a non-zero vector, yt equals to c times exponential lambda t. That will be the corresponding eigenvector. Eigenvector, and this is an eigenvalue. So there are an infinite number of eigenvalues, and this is really because T is defined on an infinite dimensional space. So you can think like this is like it's a matrix. It can be represented by a matrix. How to do that rigorously is another question. So that there are indeed an infinite number of eigenvalues. But by this very simple calculus, miraculously, we can actually find all its eigenvalues and eigenfunctions. Okay, so first order differential equations, I mean, that's it. So essentially all the linear first order differential equations can be solved in this way. I mean, this really includes all the cases. I mean, there's no other. There's a constant here, constant here. If there's a constant divided to there, and I've solved all. So all first order differential equations, linear differential equations. Are solved. Therefore, our focus is really second order differential equation. Sorry, linear differential equation with constant coefficients. With constant coefficients solved. So we really look at the second order differential equation with constant coefficients, which means a differential equation of this form. So why do we focus on the right-hand side equal to 0? Because as we said before, even if the right-hand side is not 0, we still need to study the case for the homogeneous system, and then find a particular solution, which is a business of its own, and we add them together, we find all the solutions. Again, in the linear algebra language, and we're mapping yt to y double prime plus by prime plus cy. This one equal to 0 means that we're interested in the null space of T. Any question? Let's look at the example. Solve this. Okay. How do I solve this problem? You can make some educated guess. For example, exponential T seems to be right, because take a derivative is still exponential, take double derivative is still exponential, and I get a solution. But this is not quite reliable, you know. If you always rely on guesses, makes you a little bit nervous, just like in the case of solving linear systems. If you always rely on guess, x must be 1, 2, minus 1, 5, I mean, maybe you're right, but you don't have a method to do it. Now we want to find a method to solve this linear system. The method is so-called auxiliary equation. The auxiliary equation is very simple, which is you start from y double prime minus y. You just replace everything that has a derivative by a number. Let's call it, let's say, r. So this one becomes r squared, and replace the number of derivatives by a power, minus still minus. This one, y, replaced by r to the 0, which is 1, equal to 0. Why are we doing this? We're going to explain that later. I factorize this, which gives me r1 equals to 1, r2 equals to minus 1. Okay, so I've just introduced out of the blue this auxiliary equation. Why we care about that is not that clear. Now I'm explaining why do we care about that. So we consider this mapping, which is ty. It is d squared dt squared viewed as operator minus the identity applied to yt. Y double prime minus yt. Now I want to do some factorization on the operator level. Want to do some factorization on the operator level. It's a fancy sentence, but it's a really simple thing to do. So this is d dt minus I, and this is d dt plus I yt. How do I know that? So one way to do is to just directly check. First of all, I have this one. So let's call this one, let's call this star, okay? Star equal to d dt minus I. Inside, it becomes a new function. This is an operator as well. It maps an infinitely differentiable function to infinitely differentiable function for the y prime t plus yt. Everyone's following? Any question? Good. Now I have
Sorry, wait, why is I involved?
I is the identity.
I know, but why is the identity involved in the transformation?
Which line? Here or here?
The first one.
The first one, because ty is y double prime minus y, right? Identity applied to y is y.
Oh, okay. Okay, understood. Thank you.
Any other question? So this line is very simple, but I want to make sure that everyone understands what I'm doing. If you understand, the rest of the thing will become really simple. Otherwise, it becomes complete mystery to you. Okay?
Where did the initial y double prime minus y equals 0 come from?
That's the problem. I
Oh,
asked
okay.
you to solve this problem. Any other question? Okay. So, let me see. So this one is, I take a derivative again, y double prime t. This is plus y prime t. This is minus y prime t. This is minus yt equal to y double prime t minus yt, voila. So indeed, this one is equal to that. Clear? Now, let me say why this shouldn't count as a mystery. The important thing is that DDT is an operator, identity is an operator, they commute. What does commutation mean? It means that DDT times identity applied to thing, let's call it y, equal to identity times DDT applied to y. So, so if the two things commute, then this is like in the linear algebra, AB equals to BA. It means that we can manipulate these operators as if they were scalars. That's really the most important sentence to understand this. We can do operations on this, we can manipulate these operators as if they were scalars. If they were like scalars, indeed you can see, I can just view, we can replace the operator DDT by a number R, therefore R squared minus I becomes the DDT square minus I become an auxiliary scalar equation, R squared minus 1. This is a quadratic equation. We can factorize and obtain its roots. Once we can factorize that, what is this? The factorization means this is R minus 1, R plus 1. Now we do the substitution back, replace R by DDT. So we have this. Exactly. If this is clear, then you have gone through the most difficult part. Next is why is this useful? It is useful for the following reason. Now you know Ty is equal to DDT minus I, DDT plus I, YT. To make sure this is 0, a sufficient condition is to make this 0. If this is 0, then any leading operator acting on 0 will be 0. So what does this 0 mean? Y prime t plus yt equals to 0. This is a first order differential equation. And we just said that all the first order linear differential equations with constant coefficients can be solved. We just solve that, put to the right hand side, becomes -1. So yt equal to C1, and this is a exponential minus t. We've only found one of those. What's the second one? The second one is if d dt commute with I, then these two, which is d dt minus I and d dt plus I, they commute. If you're not sure about the commutation, you can just carry out the calculation by yourself. Now, you see, although I changed the order of the two, that's trivial. Now what I can do is to make this to go to 0. This gives me y prime t minus yt equal to 0. So I have yt equal to C2 exponential t is another solution. Now I've already found two linearly independent solutions, and these are indeed all C1 exponential t, C2 exponential minus t, and these are all the solutions. Any question? Since it's a second order differential equation, there are only two arbitrary tunable parameters that you can have. I've already got two. The two solutions are linearly independent, and therefore I've solved the problem. Okay, so now let us use this knowledge and solve this.
Why is it C2E minus t? Because the answer above is C2ET.
That doesn't matter, right? So there's some arbitrary constant. Thanks, but yeah.
Oh, okay.
Yeah. So I'll ask you to solve this problem. Go to this. Compared to the example I had earlier, the only new information are these things. These things are called initial conditions. This is really different from linear algebra, because in linear algebra we didn't have a time variable there. So if I have equation together with some initial conditions for second order linear differential equation, you need both to specify both the function value and its derivative to really determine the solution, because you have two unknown variables. And this is called initial value problem. So IVP. So how do I solve this? For a general solution, I'm sorry, are you hearing background noise or not?
No.
Sorry?
No.
Very little.
No background noise? Okay,
No,
that's
you're
okay. Yeah, sounds good. So there's the general solution, and this is we have just put that we have just seen that this is minus t exponential to the t. Now I just plug it in and plug in the initial value to determine C1 and C2. So Y0 is C1 plus C2. This I told you it is 1. Y prime 0 is minus C1 plus C2. This is equal to 0. So I have determined YT without any ambiguity. And this is this. So at this step, we say that we have solved the initial value problem. Any question? Okay, so look at another problem. So y double prime minus 2y prime plus y equal to 0. So this one, again, we look at the auxiliary equation because the t, y, so this one is d squared dt squared minus 2 ddt plus identity acting on some yt. We do exactly the same thing. Replace second order derivative by r squared. This is the first order derivative plus 1 equals 0. It's rather intuitive. Now we factorize this. We get r minus 1 squared. This is equal to 0. Okay, so we carry on with the calculation. So this means that ty equals to ddt minus I squared yt. So I want to convert this to a first order differential equation. And so I get ddt minus I yt. If this is 0, then it's a sufficient condition to find a solution. So this one is yt equals to some c1 exponential to the t. Now I'm stuck. I'm stuck. Because, why am I stuck? Because I cannot play the game of exchanging the two things. I don't have a second first order differential equation. Have run out of first order differential equations. However, I know that I must be missing something because I started with the second order derivative and just to do integration and do another integration. There should be a C2 somewhere. I will provide two ways of giving you the answer. First is I claim y2t is exponential t, but multiplied by t. I'll give you a few seconds and to just do the calculation to convince you this is the solution, and then we're going to do it together.
Professor, how do you know that you needed another first order differential equation?
So that's because, as I said, think about the warm-up problem. It's a second order derivative. You just integrate once and you get a C1, right? Integrate twice, you get a C2. So at least I expect that there should be another solution.
Okay, thank you.
Let's do it together and make sure that this is really the solution. So we do y prime, y2 prime. So this one is t prime, and this is exponential t plus t exponential t, and therefore I have y2 prime t minus y2t equals to exponential t. Okay, so at this point I know I'm done. Why am I done? Because this one is exactly the y1, right? So what this is saying is, I mean, I can keep computing the second order derivative, But I've already know that ty2 equals to ddt minus I ddt minus I y2t. This calculation shows this is et, and therefore we have this is equal to 0. And obviously this one, this solution is linearly independent with the first solution. So we have y2t c2 t exponential to the t. So the solution set to the homogeneous problem is c1 exponential t plus c2 t times exponential t. Any question? Okay, so I mean, I just did the calculation here, and you have very good, followed me, go through the steps, but this t is really a little bit mysterious. How do we know that, I mean, the solution should take this form? I mean, exponential t seems to be pretty intuitive. Ddt equals to y, I just integrate, I get the exponential. But how come I have this one? Let me provide an interpretation. So this interpretation requires a little bit knowledge of the calculus, which involves taking limit. Hope you still remember how this procedure goes. It's pretty simple. I consider a modified problem plus 1 plus epsilon 1 minus epsilon times y equal to 0. So here, epsilon is a very small number. And I want to have epsilon go to 0 plus. Plus means that epsilon is a positive number and goes to 0. We realize that when epsilon is equal to 0, this is exactly the problem we want to solve, right? So this is y prime minus 2y prime, y double prime minus 2y prime plus 1 times y equals 0. Why do I want to consider this case with this small number epsilon? Is because we consider the auxiliary problem. This is r squared minus 2r plus 1 plus epsilon, 1 minus epsilon equals to 0. This one you find that it has 2 roots, right? You have these 2 roots. So the previous argument would apply. So I know that the solution would take the form y1t is some c1. Let's forget about the c's. So 1 plus epsilon t, y2t is exponential 1 minus epsilon t. And they are linearly independent because they have exponential growth but with a different growth rate. Remember that this is, let me put the epsilon here. So remember that these are solutions to the homogeneous system. Therefore, the linear combination of the 2 solutions, let's call it y2 tilde epsilon t, defined to be the linear combination of the 2, just let 1 minus 2. I subtract these 2, it's still a solution. I divide by an arbitrary number, it's still a solution. This is a solution. Any question? What is that? Epsilon t minus t over 2 epsilon. And this one, I take a limit when epsilon goes to 0. You can do a Taylor expansion. This is exponential t, 1 plus epsilon t, 1 minus epsilon t up 2 epsilon divided by 2 epsilon. This is exactly t exponential t. And therefore, at least one way of viewing this thing when you have R1 equal to R2, which is the case with repeated roots. One way to view that is really think about that as a limiting procedure. I have, you can think I have an exponential lambda t, put a lambda plus a little bit, and exponential lambda t with a lambda minus a little bit, and the linear combination is still a solution, and then you just take a limit, you find that naturally this extra t, this polynomial growth term would pop out. Any question? Okay, if not, let's stop here, and next week we're going to continue with the differential equations.